Hey guys, Mr. Betts here. I want to talk about something called the fundamental theorem of calculus. And as the name suggests, it's going to be a really important theorem. In fact, it's the theorem that's kind of credited as the discovery of calculus back in the 1600s. That's a long, fun story of a feud between Isaac Newton and Gottfried Leibniz, but I won't get into that here. But the important thing to understand is this is like what calculus is all about. And this theorem is going to connect the area problem and the tangent line problem together. So it's going to connect integrals and derivatives. So to get into it, let's first just do a little refresher on accumulation functions. So an accumulation function, remember from a couple of topics ago, is a function that's written in this form. So it's going to have an integral, which remember this integral here represents an area, and it's going to be the integral of a function. And one of the limits, usually the upper limit, but it doesn't have to be, is going to be in terms of the variable, the independent variable. So the function f of x is defined as an area of g of t. Now I'm using t here instead of x because x has to be used here and it can't really be used in both places at the same time. So the coordinate plane here we have is, instead of an xy coordinate plane, it's a ty coordinate plane. So this function is just like any other function that has inputs and outputs. So if I'm going to just make an input-output chart here. If we think about plugging x values into f of x, say 0, when we plug 0 in for x here, that's the same thing as plugging 0 in for x here. And essentially that's saying what is the area under the g of t function from 0 to 0, and the area of that is just going to be 0. And we can go through and do this with other x values. I'm just going to put some in here. We don't know what this function is, so I'm just going to make up some numbers. But if we plug in 1, that's going to be, say, the area between 0 and 1, which is going to be some value. That area is above the x-axis, so it's going to be a positive area. If we plug in, say, 2, then we're going to have an area that looks like this. Notice that that area is bigger. So f of x should be bigger than 4 at this point. Let's say it's 7 now. And so what I'm getting here is some coordinates that I could plot in an xy coordinate plane. And these points would be a function. So the graph of a function also. So this graph of f that I'm creating here, let's just look at a coordinate plane here. So 0, 0, 1, 4, 2, 7, and we can plot points in between, and we're going to get a graph that looks like this. Obviously, the graph of f of x is going to be related to the graph of g of x in some way because f of x depends on g of x. So the question then is, what can we do with this with calculus? So if we're looking at the f of x function here, can we, say, apply the tangent line problem to that? So can we figure out what is the instantaneous rate of change or the slope of the tangent line at any given point? So we're going to explore that here with this generic function g of t and the accumulation function f of x that's defined in terms of g of t. So we're going to look at this function here. F of x is equal to the integral from 0 to x of g of t dt. So we've got an idea of how we can get a graph of f of x just by plugging in different x values. But what I want to do here is I want to look at the rate of change of f. And remember, the rate of change is going to be given by the derivative. So really what I want to figure out here is what is f prime of x going to be? So what's the derivative? So we can kind of think about this a little bit more intuitively by looking at areas. But what I want to do here is explore this using the definition of the derivative. So if you remember, the derivative of f is defined as this limit. So the limit as h approaches 0 of f of x plus h minus f of x over h. And so we can take this limit here and explore what's going to happen with that if we think about what's happening in terms of the areas in our graph of g. So I'm going to start this by replacing the f of x here with f of x, so right there, and then f of x plus h is what we get when we plug x plus h in for the upper limit. So the limit that we're going to be dealing with looks like this. And so if we look at what's happening here in the graph, this area right here is given by the shaded in purplish area right here. Okay, so that's going to be the area under the g of x function or g of t function from 0 to x. This area is going to be a little bit different. So we're going to go on the x-axis to x plus h. So we're going to move over h units and get to x plus h, and we're going to find this area all the way, including that section there too. So the picture is going to look like this. So if we think about what this difference right here is going to be, if the area here is given by this, and the area here is given by this, the difference is this reddish, pinkish shaded area here. So that difference on top is going to be the area given by this right here, which I'm going to write as the limit as h approaches 0. So technically, and I'm going to do this using algebra first, that area is going to be the area from x to x plus h. So it's the integral from x to x plus h of g of t dt all over h. And I want to think of this area here a little bit less formally. I'm not going to go through an entire formal proof of this fundamental theorem, but if we look at that area right there, this area is going to be approximated by, remember we approximated areas using rectangles, so I'm going to approximate it using this rectangle right here. And so notice that I use the height of g of t here. So the height of that rectangle is going to be g of x, because the x coordinate is what we're plugging in there. So that height is going to be g of x, and the width from x to x plus h is going to be h. So that area, the area of the green rectangle, is going to be g of x times h. And this is an approximation of the area that we're representing here. However, I want to point out that h is approaching 0. And as h approaches 0, this error, I'm going to highlight the error here. So the error with our area is going to be this region right here. As h gets smaller, that area, the error area, is going to get smaller also. So as h approaches 0, this entire area here is going to get closer and closer to that area. And remember, that's exactly what a limit does for us. It says as some value approaches some number, what happens to the resulting value? In this case, what happens to this area? So in this equation right here, I can replace that top with this, because as h approaches 0, that area is going to approach g of x times h. Now, at this point, we can do some algebraic manipulation, cancel out the h's, and this is just going to be equal to g of x. So this is actually a really important result here. What that tells us is the derivative of f of x at any point is just given by the function g of x. So if I kind of clean up my graph here, I want to point out I don't have the graph of f of x here, but if we were to graph the function f of x, then the derivative of f of x at this point x is going to just be given by the value of the function itself. Okay, so in this equation right here, when I take the derivative, I just get essentially the rate function for our accumulation function. So remember, with the accumulation function, this function here in our integrand inside the integral is usually going to be a rate function. And so when we take the derivative of the accumulation function, we get the rate function. So that right there gives us what's called the fundamental theorem of calculus. This is part one, because it shows us how to take the derivative of the area function or the accumulation function. Part two is going to go in the opposite direction, how to find an area from a derivative function. So the fundamental theorem of calculus says exactly what we just went through. If f is a continuous function, And this is important because if f is not continuous, then this area right here is not necessarily going to be approximated by g of x times h. So if there were a jump discontinuity there and we had, instead of this, the function were, say, up here, then it wouldn't work. So if f is a continuous function on an interval, then the derivative is going to be given by this. Now, I want to point out that in my proof, I had a lower limit here of 0, but it can really be any constant. So if we think about what that means, everything I just did right here would be the same if I just took a section of this and got rid of it. So if we weren't dealing with this area, but I started at another constant, and as long as a function is continuous from a to x, then this is going to hold. So the difference in the area here was the key, and that difference in the area doesn't matter if we start at 0, if we start at some positive number, or even if we continue to the left and start at some negative number. Any lower limit constant, this is going to be true. So x has to be in the interval that contains a. So f has to be continuous on some interval, and then we get this relationship right here. And as I mentioned, very, very important. That's why we call it the fundamental theorem. It makes that connection between the area problem and the tangent line problem.